Hi and greetings. My name is Dayang Farzana. We are from Group 3 and in this video, we'll be presenting on our AFO project. Now, let's begin with an introduction to ankle foot orthoses or AFOs and their clinical relevance. First of all, what are prosthetics and orthotics? Any internal or external device that replaces lost parts or functions of the neuroskeletal motor system is referred to as a prosthetic. On the other hand, orthotics refers to assistive tools used on the body's exterior to reduce pain or boost the functionality of the limbs. One commonly used orthotic device is the ankle foot orthosis. An AFO is an external orthopedic device worn around the ankle and foot to support, align, or correct deformities, as well as to improve overall lower limb function. AFOs are widely prescribed for individuals with gait abnormalities, particularly those experiencing foot drop, where insufficient ankle dorsiflexion causes the foot to drag during walking. In such cases, an AFO helps stabilize the ankle and promotes a safer and more efficient gait pattern. From a biomechanical perspective, the ankle primarily performs plantar flexion and dorsiflexion, while the knee functions through flexion and extension. These joint movements are closely linked during walking, meaning that controlling ankle motion can also influence knee stability. Clinically, this highlights the need for an AFO design that provides ankle stabilization while supporting coordinated lower limb movement. With these considerations in mind, our project focuses on the design and fabrication of an AFO that addresses these clinical needs.
Hi, my name is Erdina. The objective of this group project includes to fabricate a functional ankle foot orthosis. Secondly, we are to apply theoretical knowledge while sharpening our practical skills as well as getting the exposure. Next, we are to do analysis on the final product, and lastly, we get to build teamwork among group mates throughout fabrication process.
Guys, I'm Chung Zhen, and now I'm going to present the part of the methodology, which is the part of the user and clinical requirements. So basically, we are targeting for the users with 18 until 65 years old, and also with the activity demands from low to moderate to optimize the cost and the design of the AFO. And also, we have the expected specifications as shown in the table, and we are analyze the specifications from range of motion, weight capacity, material properties, the life cycle and durability, at which how many gait cycles we can do, the device weight to prevent overweighting, and the power wasting of the user, and also the practical usability is how easy the user can don and doff the AFO. At this part, you can see our initial draft that was created by me and my teammates, and yeah, have a look. Okay, so after the discussion with my teammates, our team come up with the finalized geometry and the design of the AFO in 4 types of the perception. So the first one is the overall shape, the second one is the trimline, the third one is joint mechanics, and the fourth one is strapping. For the overall shape, we use the PLSO geometry, at which we put the strap on the upper side of the AFO, which is the proximal side of our tibia. Then we have the trimline, at which we cut the trimline follows the anatomical outline, at which the users can have a smoother experience and also prevent the injury when it dons and doff. After that, for the joint mechanics, we plan to have the function as the non-articulated AFO, at which we need to limit the range of motion of the joint so that the regeneration and also the recovering of the joint will be faster. So lastly, for the strapping, we decided to use the Velcro strap due to the low cost and also the high durability. That's all. Now, we are going to talk about the most important thing in our product AFO, which is the selected material for its overall body, which is thermoplastic. So why? There are 3 reasons here. So firstly, it will be sufficient flexibility for the users to undergo the gait, at which it can control the range of movement but not zero overall. And secondly, it's cost efficient. It's not like carbon fiber that is very expensive, but it also has the moderate durability, at which it can consist of high amount of the gait cycles. And you can see about the properties of each thermoplastic, which is PP, PC, nylon 6/6, and also the PMMA at the table.
Moving on, these are apparatuses used for ankle foot orthosis fabrication and criteria needed for subject selection. For casting, tools and materials needed include plaster of Paris bandage and powder, stockinette, plastic tube, marker and cast saw. For thermoforming, material used is thermoplastic sheet that need to be heated in the conventional oven and shaped using vacuum forming machine on the positive cast later. The finishing process involves trimming and smoothing using grinding machine. And lastly, for the subject, we are advised to choose subject with smallest leg circumference among group members for easier handling. Next, also part to be covered in the methodology, fabrication starts with getting the measurement. This is fundamental to get a perfectly fitted orthosis. We start off with measuring the curve circumference by determining the proximal point. From that, we leave a gap of 2 cm from the proximal and start marking 5 cm interval points until we reach the distal. Next, we get the total length of the leg from the proximal mark earlier to the heel. After that, we also measure ankle circumference followed by foot length and foot breadth. Once measurements are taken, we proceed with negative casting. First of all, it's important to position the foot by ensuring that the subtalar joint locked in neutral while mid-tarsal joint fully pronated. Before positioning, the subject was ensured to wear protection layer as in stockinette, and also a clear tube was inserted inside it at the front part of the leg for safety during cutting process later. Next, plastering begin by wetting the plaster of Paris bandage and then wrap around subject's leg until fully covered. Once done, we let it to dry for a few minutes. Before cutting, we ensure to check if there's any adjustment needed to prevent uneven wrapping. After that, we begin cutting the negative casting through the tube inserted earlier on.
The next stage of the AFO fabrication is the cast filling stage. First, a metal rod was inserted into the negative plaster cast to provide internal support and maintain alignment. Any openings at the base of the cast were sealed to prevent leakage. A plaster mixture was then poured into the negative cast and left to dry. This is a relatively quick process, resulting in a solid positive cast that represents the subject's lower limb anatomy. Once the plaster had fully set, the negative cast was carefully removed, revealing the positive model. The surface of the positive cast was then smoothed to remove surface irregularities and ensure accurate anatomical contours. Accurate measurements were checked at this stage, which involved confirming that the dimensions of the positive cast matched the subject's lower limb measurements, as some areas may have been reduced during grating or damaged during negative cast removal, requiring additional plaster to be reapplied and reshaped accordingly. Then, nails were inserted along the toe edges of the positive model. A flexible plastic strip was placed in front of the nails, and plaster was added into the hollow space between them. This step was performed to create a smooth, flat toe edge, which helps define the trim line and improves the final fit and finish of the orthosis. The added plaster was then smoothed and refined to complete the modified positive cast.
Hi Dr. I'm Chen, and thank you for my teammates for presenting the previous methodology, and now I will continue with the thermoforming. So next is the thermoforming process. The modified thermoplastic sheet was heated in oven around 180 degrees Celsius for about 10 minutes until it was fully softened. It allows the material to easily mold without damaging its properties. So the softened thermoplastic was then vacuum formed into the positive cast, and the excess air was removed from the gap. After that, the plastic was left to cool until it solidified fully before we move to the finishing stage. Alright, so after the thermoforming, the plastic mold was further processed to form the actual AFO, which is the ankle foot orthosis shape. The trim line was first marked using the marker pen, and we carefully cut it, the trim line, using the cutter. The step will be done slowly to avoid the mistakes in the shape. So the edge, and then we sanded using the sanding machines with the different toughness, and followed with the sandpaper to smooth the edge. So this will improve the comfortability and to prevent the injury when the users wear and use the AFO in a long time. Alright, so before we give it the AFO to the user, we need to do the product assessment. So how we do it? The product assessment was carried out to evaluate the performance and the comfort. Yeah, we know that. And the dimensions of the AFO were measured again and compared with the user's leg to make sure that the compatibility is high. And the user was then perform the several tests by using the new AFO prototype, including standing still, walking at a normal speed, and also giving some feedback on the comfortability. So this step is very crucial to ensure that the AFO doesn't cause the discomforts and also the fitting problems when they use it for a long time in the future. Hi, so in the product part, I will be the presenter and I will present 3 parts in this product, which is the initial measurement of the modeling limb, the specification of the AFO product, and also the visualization of the product AFO. In initial measurement, we make it in 3 views at the slide, which is the medial view, the posterior view, and the plantar view. So we included the measured parameters, which are the circumference in the medial view, the radius of the leg at the posterior view, and also the width and the length of the foot at the plantar view. The specification of our AFO, actually we found that the size, which is in terms of the circumference and the inner diameter, is quite similar to our initial measurement of the model. So overall, we found that the AFO is quite fit to our model, and then we can see the overall specification under the table here, and we know that the total AFO length is around 33 cm, and this will not going to limit the range of movement, which is the ROM of the model's knee. At this slide, I attached the engineering drawing in 2 dimensions to show that the model of our AFO product. Hi, so now I'm going to show that our 3D model of the AFO, and we scan our model into the 3D form in the STL file, and we uploaded onto the website platform, which is the Sketchfab, and now I'm going to show you the 3D model in this platform. So basically it's like this: behind, front, okay, down here, and then in front, and then the side also. Okay, so that's all for our 3D model, and for more information you can click on the link in our report to show more details here. Thank you.
Analysis was done on the fabricated ankle foot orthosis. We evaluate based on performance, structural and mechanical properties. It able to maintain ankle in neutral position while improve walking speed and stride length. For recovery, that qualities considered a good one to improve alignment and stability of a patient. Other than that, it has adequate rigidity while also being lightweight to ensure long-term structural integrity and minimizing weight for patient comfort. Next, there are a lot of types of ankle foot orthosis in the current market, so we ought to compare ours with the existing design. We take, for example, articulated foot orthosis in comparison with solid foot orthosis, the one that we fabricated. In terms of design, articulated foot orthosis comes with hinge to facilitate the ankle motion. Though it sounds more advanced, it is proved to be less stable. As for solid type of foot orthosis, it has no hinge, means it will restrict ankle motion, but it is more stable compared to the articulated one. In this project, we aim to keep it simple for better recovery while bringing comfort towards the patient.
It's me again. So I will perform the presentation on this part, which is the fabrication process evaluation. So in this part, we main focus are the casting, the thermoforming, and the finishing process. So the accurate casting is very essential to ensure the good anatomical fit, and error at this stage will affect the entire size and the fabrication process. Next, during the thermoforming, the uniform heating is very crucial to avoid uneven thickness. So it can reduce the stiffness and the durability if we do so. And lastly, the finishing also plays a very key role in the comfortability, as a proper trim line and the smooth edges will reduce the pressure and the injury risk. And overall, although this conventional method was depending heavily on the operator skill, but it will still used widely in the society and the market because it has a low cost, customizable, and a clinical relevant properties. Lastly, in terms of the design effectiveness and the clinical relevance, the AFO was able to provide ankle stabilization and maintain near neutral ankle position. So this will help the user to prevent the excessive plantar flexion and improve the guide safety. The thermoplastic AFO are widely used in the hospitals and also the P&O stations because they are very affordable and it can be reshaped during the rehabilitation. The smooth trim lines and the round edges also improve the user comfort, which is important for the long-term compliance and also the successful clinical use.
This slide shows the possible errors during the fabrication of the AFO. Some errors may come from manual measurements, such as tape misalignment or inconsistent tension. In addition, uneven plaster thickness during negative casting and non-uniform heating during thermoplastic forming may affect the final shape. These errors can cause small dimensional differences and may influence the fit and comfort of the AFO. To reduce these errors, several precautions were taken during the fabrication process. Measurements were repeated and cross-checked by group members to improve accuracy. Guidance from the laboratory PIC was also provided during casting and modification. During finishing, careful trimming and edge smoothing were performed to improve comfort and usability. This slide compares the conventional fabrication method with the 3D printing method. The conventional method is low cost and allows hands-on customization, but it is highly dependent on operator skill. In contrast, 3D printing provides higher precision and better repeatability, with less human error. However, it requires higher equipment cost and longer preparation time. There are several limitations in this project. Only one model was used and no mechanical testing or dynamic gait analysis was performed. For future improvement, multiple subjects, 3D scanning, and gait analysis can be included. Overall, a functional and cost-effective AFO was successfully fabricated and demonstrated effective ankle support and gait assistance.